Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss the types of motion. So these types of motion of fluid we'll consider for when the fluid in kinematics. So when the fluid in kinematics, that means when the fluid in motion, the fluid can be moved in any directions. Okay, it can be moved in x direction, y direction, and z direction, and also the motion also will be varies for that fluid. So it can be moved to any of the directions, or it can be formed in any of the forms. So what are the forms can be generated, or what are the forms possible formation will be there? So let's discuss about that one. So actually basically these types of motions are actually categorized into four types. So first one is the linear. First one is, let me write this one. So linear translation. Linear translation. This is one movement. Second one is the same thing will be there, but linear deformation will be there. This is translation, and second one is deformation. Linear deformation. And third is angular deformation. Third is angular deformation. And fourth one is rotation. So these are the four different types of motions are there. This is rotation. First one, second, third, and fourth. So linear translation also used to called as a pure translation. Also it is called as pure translation. So both are same actually. We can call linear translation, or we can call as a pure translation. Okay, and linear deformation, then angular deformation, rotation. Let's discuss about these four of these points in this lecture. So first one we will discuss about the linear translation. So linear translation actually when the fluid particles, okay, we can here I have given here this example. If you see, this is the diagram for the linear translation. So initially the fluid particle is, suppose the fluid particle is this, and it is a definite shape we have taken here. And if you see this fluid particles, initially this condition is there. Or let me draw another one diagram. Suppose this is the diagram is there, and this is x-axis, and we can show this is y-axis. Okay, the same thing, just I will draw in different way. First, when the fluid particle is there here, let's suppose this is the position of this fluid particle which is present here. Okay, and this fluid particle we can mark it like what are the marks are there here. Here also I'll just give the same thing. I'll just give it at this point A, B, and C, D. Okay, now after the changes, okay, after some changes happened, like the fluid moved from this place to some other place. Okay, there is a translation happened, linear translation happened. Okay, so in this linear translation, this fluid particle will be moved from this position to some other position. Suppose it moved to here. This is the new position of this fluid particle. So initially it is denoted as A, B, C, D. Now after that it can be marked as like A dash, B dash, C dash, and D dash point. So these are the new point after this changes happen, translation happen, linear translation happen. So what we can say, this linear translation actually, it can be defined like the movement of a fluid element, in such a way that it moves, the total body, okay, it moves from one position to another position. This is initial position, and this is after movement of this fluid particle to the next position. So this is starting initial, and this is final position. That means from one position to another position. Okay, and the axis, if you see, what is the axis of this object? If I draw the axis of this object, it will be like this, x-axis, and this will be y-axis. Okay, so the axis of this object, if you see the axis of this, I can give a x-axis, or I can give a, this is y, let give, because it is in y direction. So let's give this is y only. Keep this y, and this is x-axis, we can mark it. So the axis x-axis and y, okay, represent the new position will be what will be there. If I represent that one, so what will be there here? Now y dash, and this will be x dash, and x does. Okay, so this is the new form. But if you see, these axes are not changing anything. That axes are all are parallel to each other. Thus here also same things are given. Okay, these are the axis lines. AB are the axis line in the x direction, CD are the axis line in the y direction. And after changes happen, A dash B dash. If you see, this AB and A dash B dash both are parallel or not? Similarly, CD and C dash D dash both are also parallel. So in the linear translation, the fluid particles what is moving, like it is changing its position, but the axis of these fluid particles will be remain same. So that is the linear translation, or you can say the pure translation. Next is linear deformation. Okay, the linear deformation is nothing but it is also simple. If you see, this is the diagram what I have taken from the book. So in the linear deformation, if you see, initially the object is, suppose, this is the object is there, which is not visible here. That means it is already hidden here. Okay, now in this, if you see, initially the starting point of this object, so if you want to draw again, I can draw a diagram here similarly. So this is the x and this is the y, and just draw a diagram like this initial starting. Okay, similarly we can just give the point of this fluid particles, like this fluid element, we can mark it AB, again similarly AB and CD point. Now in this deformation means it should be changed. Some deformation should be happen either in the lengthwise or height-wise. Okay, when the deformation should be happen, that now if you see, after deformation happened for this fluid particle, it is going to change its position. Okay, now it's going to change like this. Let me draw in this way. Okay, so now what are the changes happen? The changes happen in the y direction also, in the x direction also. So after changes, we can write this is C dash and this is D dash. So what are the changes happen? In the y direction, there is a change in dy, suppose, and in the x direction we can say there is a changes in dx. So these are the changes happen in the fluid particles. So here are the same thing, just marked here. But if you see, the base point of this, it is not going to change here, the A point. Here also again, if you write here A dash, now B point is going to change it, so you can write this is B dash point. Okay, now there is a changes happen, distance, how much distance is changed. Okay, so that we can mention here. So basically when you are going to define this linear deformation, so how we can define this linear deformation? So you can write that the linear deformation is defined as the fluid element in the linear direction. Obviously in the linear direction it is moving in the linear direction when the element moves. When the element, that means when the fluid element is moving, it is moving in the linear direction. And the axis, if you see, this is the axis of initial starting one, and this is the axis of this. Okay, and the axis of this element in the deformed position, okay, and undeformed position, deformed position and undeformed position, both are parallel. If you see, this is the axis for this, that means CD. After deformation, what? The C dash D dash, both are parallel. Now similarly, if you see, this is the AB axis for the starting one, and after deformation, A dash B dash. So even if you see, both are parallel to each other. Correct. Previously also we have seen, this is the parallel condition, here also parallel condition. But here what will happen? The distance or the length of this body, initially what the length was there, what the height was there, that is going to change in this case. So that is linear deformation. Okay, this is the case of linear deformation. Now next we'll go for the angular deformation. Now for the angular deformation, if you see, there is a changes happened here. Initially, again, if you see, this is the starting object is there, and the object is going to change its, it's going to deform. The fluid element is going to deform with angularly. Okay. Now here also, I can give you another one diagram for this. Okay. So let's draw one more diagram here. So this is the x-axis and this is y-axis. Again, similarly, let's consider a fluid element here. Okay. So this is the fluid element, what is there, and here also you can mark this AB and CD. This is the point of this fluid element. Now when it is going to be angularly deformed, okay, this point along with this, it is going to change. So after changes happen, okay, how it is going to change? Let draw another one axis here. Okay, this is another one axis line. Let's draw it here. And this point, this A point, it will be started from here only. This original point will be there as usual. Now this fluid element is going to change in this way. See, this is the A and this is suppose B. Now it is B dash, and it is going to change along with the x-axis. X-axis changes. Again, also it is going to change in y-axis. That means the changes or the deformation will happen in both the directions. So this is the angle, this is one angle. How much changes happen? So that can be considered, here it is given. If you see the angle after changes for the angle. So here also I can write here ABCD is there. Here also if you want to write, just you can write here A dash, B dash, and this is C dash and D dash. Okay. Now what are the changes happen? This is delta theta 1 and we can consider this is delta theta 2. So this is the changes happen in this angular deformation. Okay. If you understand the deformation, so angular deformation also you can understand with some angularly it is going to change its position. So how we can define this angular deformation? We can define that the average change means what the angle changes happen in this x direction as well as y direction. The average change in angle is contained by the two adjacent sides. So how much angle changes happen in this side and how much angle changes in this side. Both average we need to consider here. Okay. So suppose this is the delta theta 1 and delta theta 2 what we have taken. Okay. So delta theta 1 is angle changes happen in this x side and delta theta 2 angle changes in the y side. Okay. So now we can write the angle deformation rate. So that we can write here the angular, we can write some equation here, angular deformation rate. So what we can write as per the definition, we can write the average of this, that must half of this delta theta 1 the angle in this x side and delta theta plus delta theta 2. Any angle you can give it. We can give it alpha here, we can give it beta here, theta phi, anything we can give it here. So average of that. Okay, as per the definition we can write this is the average of this angle which is in the two adjacent side. So these things we can write. Now if you see in the delta theta 1 also we can write this delta theta 1 equal to, we can write delta theta 1 equal to, okay, this we can write del V by del X, del V by del X. And similarly delta theta 2 we can write, okay, here delta U by delta y. Now if you see what are the changes happen, see along with the, this is the velocity v. Here we can consider the velocity which is moving in the x direction and the velocity moving in the y direction. So we can write delta theta 1 equal to the delta v by delta x and delta theta equal to delta u by delta y. Okay, so u and v are the velocities and x and y are the components, like the directions of this fluid. So again, if you want to write the deformation rate, we can write in this way. Just put the value in this equation. So we can write that angular deformation rate equal to, we can write half into this value del v by del x, and here we can write del u by del y. Or else we can write, see, we can consider this del u by del x and del v by del y. There is no problem in that. We can consider which velocity you are considering the x direction or which velocity you are considering the y direction. It depends on that. Okay, so there is no matter of or they will be confused like v here, x here and uy, because basically we used to consider along the u direction we need to consider only x. Okay, but here we are taking the what are the changes happen in the both directions. So there is no problem in that by considering this one. So this is about the angular deformation. Similarly, the next one is, as I told you, the last one is, this is rotation one. So rotation one, actually, if you see, the rotation part is like, how much it is going to rotate along with the axis. So initially, if you see, this is the position of this fluid element, and after rotation, this body, this position is going to rotate with some angle again. So it can define this one. That is how we can define this. Now we can define it is the movement of a fluid element in such a way that both the axis, okay, both the axis means the horizontal as well as the vertical. This is the horizontal axis. Let me draw, and this is the vertical axis. Okay, so both the axis is going to be changed or is going to be rotated. Okay, but it is going to rotate in the same direction. Now initially it is there, now it is going to rotate. Suppose it is in counterclockwise or anti-clockwise it is rotating. That means if you see this axis, x-axis, that AB also rotated, it changed to this like this, AB, A dash, B dash in this way, you see, and BC, the CD also changed to C dash, D dash. So both the axes are rotated here. Okay, so here also we can write, it can be written like, half, you can write in this. So you can write this equation like, half into del V by del X minus del U by del Y. Okay, this is for the only, I'm writing for the two-dimensional flow only. Okay, now if you write the rotational component for this, that also you can write, the rotational components will be, so let me draw the line here. The rotational component of this we can write, suppose omega x. So as for the formula we can write 1 by 2 del W by del Y minus del V by del Z. Okay, similarly omega y, again we can write 1 by 2 into del U by del Z minus del W by del X. And similarly we can write omega Z equal to 1 by 2 into del V by del X minus del U by del Y. So these are the rotational components in X, Y and Z direction. But here we have taken only X and Y direction, so we can consider this two only. Okay. So this is about this rotation part. Why I told these 3 points, because one more term is actually there, that is, this is rotation. So one more point is there, that is vorticity. Okay, so for discussing this vorticity only, I have taken these 3, all these directions. So vorticity actually it is defined as the value of this, the value of this rotational, that means rotational component what we are giving here, suppose omega here we are giving. So vorticity will be defined, this is the twice of the rotation. Okay, twice of this rotation we need to consider, that is vorticity. So how we can write this vorticity? This vorticity actually it used to indicate by like summation type will be there, or you can say chi it is. This is chi equal to, we can write 2 into omega, 2 into omega, or we can write this is, if you want to calculate, so you can write, root over of omega x square plus and omega y square and plus omega z square. This is about the vorticity, which is defined, at the value twice of the rotation. Okay, so we can write this is chi equal to 2 omega. This is rotation part, and this is vorticity, and this is your angular deformation. Okay, and in the first we have seen the linear translation and linear deformation. So this is first one, second one, and this is 1, 2, and this is 3, and this is 4, and the vorticity is the next one. So I hope you understand what are the types of motions are there and why it is required. So when the fluid will be in the motion, So it can be moved in any directions, any kinds of flow will be there. So for that, like how the fluid is deforming, whether it is deforming the linearly or angularly, or it is rotating. So for that, we can use this concept. So I hope you understand. If you're having any kind of query and doubt regarding this, you can give a comment on the comment box. Thank you all.